Okay, so next up we have Vaisakh Mannalath from Universidad de Vigo. Vaisakh, take it from here.
So hi everyone, I'm Vaisakh. I am from the University of Vigo as part of the Vigo Quantum Communication Center. And today I'll be presenting some results on entanglement distribution routing in quantum networks. You can see the archive identifier here or use the QR code. Throughout this presentation, I'll be using the graph state formalism. So this allows us to represent quantum states as graphs, like as shown here. Let's see. Yeah, as shown here. And we can represent the vertices as the plus state and the edges connecting as the controlled Z gate. And this allows us to convert from graph to quantum state and vice versa. But not all quantum states can be represented as a graph, but given any graph, a symbol graph like this, you can convert it to a quantum state. And any Clifford or Pauli measurement in quantum state can be represented as graph operation in the graph state formalism. So fortunately, there are only two graph operations that we need to be concerned about. Those are the local complementation and the vertex deletion. So first, local complementation. Throughout this talk, I'll be representing local complementation operation as the as a green circle around the black vertex, and I'll be mentioning it as the LC operation for short. So here we have an example of an LC operation. So LC operation applied on this vertex is actually a complementation of the neighborhood graph of this vertex. So the neighborhood of a graph is the set of vertices that is connected to that. Neighborhood of a vertex is the set of vertices particular vertex. So in this case, the neighborhood is this vertex, and this vertex. So what we are essentially doing is combining this graph with the complete graph on the neighborhood vertices. So I'm representing here is a modulo addition. So if there is an edge in the original graph, we'll remove it, and if there is not an edge, we'll add it. So in the original graph, there is this edge here, but in the complete graph also there is an edge. So we'll remove this from in the final graph. And likewise, we can obtain the local complementation with respect to this vertex. And the next graph operation is the vertex deletion. I'll be representing it using this red circle over this vertex, and I'll be mentioning it as VD operation for short. Vertex deletion is straightforward. You just delete the vertex and all the edges connected to it. So delete this vertex and all the edges connected to it, right? And as I said, any Clifford operation or Pauli measurement on a graph state can be represented using some sequence of these two graph operations. So there will be many such operations, but they will be restricted to these two operations, right? So these are some examples of graph states. Throughout this, mainly focus on GHC states. So GHC states can be represented as complete graphs in the graph state formalism. So here we have the bell pair with two vertices, and we have the GHC state with three vertices. Also, we can convert from a complete graph to a star graph by using just one local complementation on the central node of a star graph. So if we apply this local complementation here, we'll get a complete graph. If we apply a local complementation here, we'll get a star graph. So the peculiar thing is that for two-party and three-party GHC states, the graph state formalism gives us the line graph as the graph corresponding to the GHC state, right? So our concern, okay. So yeah, we have the Pauli measurements and how to represent the Pauli transformations. So first is a Z measurement. We can just represent it as a vertex deletion on that particular vertex. So in which vertex we want to perform Z measurement, we perform a vertex deletion. For Y measurement, we have a local complementation followed by a vertex deletion. So I'm representing here a green circle, stands for the local complementation, and then a vertex deletion operation. The X measurement is a bit more complex. It's a Y measurement sandwiched between two local complementation, but this local complementation is applied on a different vertex W from V. So W is a neighbor of V. So the choice of neighbor is random. We can choose any neighbor, but you have to stick with the same neighbor for these both of these local complementations. So now we have the necessary ingredients to start stating our problem and our subsequent solution. So the problem that we are interested in is entanglement routing. So given an arbitrary graph state and given a subset of vertices, let's start with the simplest example, two vertices. How do we establish a link between these two vertices? Now, if these two vertices were connected, we could have just deleted all the other vertices and ended up with the entangled link. But these are not connected. So how do we manage to connect them? For this, we just we choose a subset of vertices and delete them so that we have a path between these two vertices. So if we choose these three vertices and delete them using Z measurements, we have a path between the vertices 1 and 2, likewise. And then if we perform Y measurement on the other vertices, like these two vertices, then this will eventually connect 1 and 2. To see this, see that, let's focus on the local complementation operation here. So this will connect this vertex and this vertex. This green circle will here connect this, and then the red will remove this vertex. And then we perform Y measurement on this. This local complementation will connect 1 and 2, because 1 is now connected to this vertex. And then the red will remove this vertex, and 1 and 2 will be connected, likewise. What about if we choose 3 vertices? So now we want to connect 1, 2, and 3. Remember that GHC state for 3 vertices is actually a line graph with these 3 vertices. So we just need to find a path connecting 1, 2, and 3 by performing some measurement on the other vertices. So now if we choose these 3 vertices and remove them from the graph, we'll end up with a line graph connecting these 4 vertices. Now we also need to remove this vertex. We can perform just an Y measurement as before to connect 3 and 1, and then remove this like this vertex using some measurement, and we'll have the GHC state connecting these 3 vertices. Now the natural question is, how do we go to beyond 3 vertices? Like, how do we connect 4 vertices or 5 vertices? Right. So far we've used the technique of connecting, finding a connecting line graph with 2 or 3 vertices to get the eventual. And in a connected graph, finding such a path is always possible. So that's good news. But the bad news is that for n greater than 3, this trick won't work. To see this, look at the line graph with 4 vertices. We cannot use any sequence of this graph operation that I mentioned before to get from here to here. So this is the GHC state with 4 vertices, and this is the line graph with 4 vertices, and no sequence of local complementations can end up here. So this trick won't work here. And of course you can ask, like, this is a simple case of line graph. In general, graphs are very complex. There will be other vertices connected to these graphs. Maybe if we apply some local complementations on other vertices, maybe we can end up here. But the ugly truth is that solving this problem for like arbitrary graphs is an NP-complete problem. It's a vertex minor problem, and recently it has been shown that this is an NP-complete problem. So it's that there will be an efficient solution for the general problem. So what we are interested in was finding some subset of such problems where we can find an efficient. And our solution is based on just one condition that we can impose on the graph state, and if that graph state satisfies that condition, then we can construct any GHC state from that graph. So our protocol is known as the X protocol because it's mainly relies on the Entanglement. And the condition is that the final vertices that are to be included in the final GHC state should be non-adjacent. So what I mean by non-adjacent is that the vertices should be connected initially by an edge in the original graph. And if the graph state satisfies this condition, then we can construct a GHC state using this protocol. So this protocol is just basically 2 steps. You find a suitable path connecting the final vertices, and because of this condition, there will be an additional vertex between every couple of final vertices, and we can just perform X measurement on those additional vertices to end up at the final product. So here's an example. We have a line graph with 7 vertices, and we want to construct a final GHC state between this, let's say, the odd vertices. And if we just perform X measurement on the even vertices, we'll end up with a complete graph. So the result seems very simple, but I'm not going to explain here why this is true or like how do we end up here, but this is the main result. And this condition that we need additional edges with additional vertices between every other vertex can be relaxed at the ends of the line graph, because of this, you just need one additional vertex for constructing a 4 GHC state. And so far we have only seen examples of line graphs, but this works in arbitrary topologies. So here's an example of a grid graph, and we want to construct a GHC state between the red vertices. So we can just remove these shaded out vertices using Z measurements and construct such a path, and then perform X measurement on these vertices to end up with the GHC state. And after we publish these results, there has been a couple of new development in this result. And if these people from TU Berlin actually proved that the protocol that we use to construct this GHC state is the optimal solution for a line graph. And this was something that we tried to prove, but they actually proved it. So that was nice. And in our work, we only considered operations, but it also works with noisy states, and this group considered it as an entanglement distillation and showed its advantage against distillation protocols. And that's it. Thank you.
Okay, we have plenty of time for questions.
Yeah.
Can you raise your...
Talk. Can this be applied to other types of entangled states, like cluster states, for example?
Yes, I mean, like any type of state represented as graph states, we can use this result. Yes.
Graph states in
Yeah.
general.
I mean, no, it's like
Okay.
Yeah.
Thanks.
You have a question?
Hi.
Hi.
For the talk. I was wondering, when you talk about n in that slide in the beginning, well, not in the beginning, in the middle.
This
yeah,
one,
there.
yeah.
You're talking about n, the size of the graph, or n, the size of the entangled state you are targeting?
The size of the final GHC state. Yes.
Sure. And if you have like an arbitrary graph,
Yeah.
and the last state is just only has 2 or 3 nodes,
Mhm.
then it's always possible and efficient.
Yeah, it's always possible and efficient. Yes.
Okay. It's yeah.
Yeah.
Surprising to me.
I mean, it has to be a connected graph. So, I mean, if it's disconnected, then it might not be possible. But if it's a connected graph, it's always possible. And it's like easy to see why, right? Because if you have like such a graph and like some vertices here, we can always find a path because it's connected. And if we can always find a path, then it's always possible to remove the other vertices and disconnect this path and then perform some measurements here to connect this and this. It's always possible. Yeah.
Okay, thank you.
Maybe one final question.
Given you can know what's the best option to create the entangled state, but if you don't have the graph, let's say you want to build a quantum network with some nodes, how difficult is it to find the optimal connections between the nodes to have the best possibility to create entangled states between them?
Yeah, right. So I guess in the quantum network field, this is known as having a global link knowledge, like having an understanding of what the global state looks like. So that's this problem. There's also this problem of local link knowledge, where like every vertex is only aware of which vertex it is connected to, and we don't know like what the other relations look like. So in that case, this becomes like a probabilistic problem, and the solution will be to find the path which kind of optimizes all these probabilities, like find the path which kind of increases the probability of having a GHC state. And this problem has only been solved for 2 and 3 party. For multi-party, it's still an open problem. Yeah.
Also, it could be generalized to not having the same efficiency in every node. Or
I didn't get in there.
like if you have some faulty node in the network that doesn't work as efficient as the rest of the nodes, it could be generalized.
No, I mean like if you're talking about like 2 and 3 party states, the problem is efficient. Trying to find a solution is efficient. I mean like you don't need additional knowledge. But for multi-parties, even for this solution, it cannot be extended naturally to the local link knowledge level. There is no efficient solution as of now. Yeah.
Thanks.
Okay, so thank the speaker again.